So we've seen in previous videos the definition of sine, cosine, and tangent, and we've also justified why the definition doesn't depend on the size of the triangle that we draw, but only on the angle that we're applying it to. And I want to use this knowledge to develop a table of some of the most common values of these trigonometric functions. So I want to do it for 0 degrees, for 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And actually 45 degrees is something that we've already looked at in a previous video. That was where I drew a triangle of side length 1 and side length 1, a right angle triangle, which then gave us the hypotenuse side length √2 by an application of the Pythagorean theorem. And so we get this theta, which is 45 degrees, by the symmetry of the triangle, gives us a value of sine of 45 degrees, opposite over hypotenuse, that's 1 over √2. Cosine, adjacent over hypotenuse, also 1 over √2. And tangent, opposite over adjacent, that's 1. So we get that the sine, the cosine, and the tangent of 45 degrees are given by these values. And once again, we've justified the fact that as long as this angle is 45 degrees, it doesn't matter that I picked the triangle to be easy to work with, to have side length 1 and 1 rather than some different side lengths. The ratios are only are entirely determined by the angle here. So we can also use that to get values for 60 degrees by considering an equilateral triangle of side length 2. Of course, in an equilateral triangle, all of the internal angles are 60 degrees. Now, this is not a right angle triangle, but by dropping a vertical line down from the top here, I get a right angle triangle. So I'll copy this right angle triangle, I'll copy it over here. What are the side lengths? Well, this one is 2. This is 60 degrees. This length here has to be 1 because it's half of the base. And that tells me that this length, which is h, again by the Pythagorean theorem, I get 1 squared plus h squared equals 2 squared. And that tells me that h squared equals 4 minus 1 equals 3. So h equals the square root of 3. Now I have a right angle triangle with a 60-degree angle, and I can use it to calculate the sine of 60 degrees. That's opposite over hypotenuse, so the square root of 3 over 2. The cosine, that's of 60 degrees, that's adjacent over hypotenuse, so 1 over 2. And the tangent, opposite over adjacent, so √3. And actually, since we know that the interior angles of a triangle always add up to 180 degrees, since this is 90 and this is 60, this has to be 30, so we can get this column as well. Looking at the perspective of the triangle, the right angle triangle from this angle now, we have the sine of 30 degrees is opposite over hypotenuse, that's half. The cosine of 30 degrees is adjacent over hypotenuse, that's √3 over 2. And the tangent of 30 degrees is is opposite over adjacent, that's 1 over √3. Okay, that leaves these two special angles here, 0 and 90. And those are special because you can't really draw a triangle where the angle is 0 degrees or 90 degrees, right? Let's draw a triangle, a right angle triangle, with a really, really small angle. So this theta is really small, it's kind of close to 0. And you can kind of see that as I get closer and closer to 0, what happens is the opposite side gets closer and closer to being nothing, and the adjacent and hypotenuse side get closer and closer to being the same length. Right? So we could write that, this is just an intuition, but as theta goes to 0, again, just an intuition, opposite side goes to 0, and the adjacent side goes to be the same length as the hypotenuse. Just just judging from this picture. Now, this is, again, just an intuition. We'll formalize this in another video. But this intuition suggests that the sine of 0 degrees, opposite over hypotenuse, should be 0. Because the opposite is getting arbitrarily small, getting close to 0. The cosine of 0 degrees, adjacent over hypotenuse, well, these are getting closer and closer to being the same thing, so this should be 1. And the tangent of 0 degrees, opposite over adjacent, should again be 0 for the same reason that this was 0. And finally, if we look at a right angle triangle where the angle is approaching 90 degrees, so we've got our right angle on this side, and what I'm doing is I'm drawing a triangle where the angle on the bottom left here is getting closer and closer to 90 degrees. And now I see something is happening kind of like the opposite of this. The adjacent side is getting shorter and shorter, and the opposite side is approaching the length of the hypotenuse. So we can fill in this column using our intuition based on the fact that as the angle of the triangle gets closer and closer to 90 degrees on this side, the opposite and hypotenuse side get closer and closer to being the same length, and the adjacent side squishes closer and closer to 0. So sine, which is opposite over hypotenuse, should approach 1. Cosine, which is adjacent over hypotenuse, should approach 0. And tangent, which is opposite over adjacent, so the opposite side over the adjacent side, should approach however long the opposite side is, divided by however long the adjacent side is, which is like 0. So this entry in the table looks like it requires us to divide by 0, which sometimes we might think of this as being something like infinity. Right now I'll put it as a question mark, and we'll formalize the values in this column in another video. But here we have, at least in the center here, the common trigonometric ratios for these three angles, and the sort of inferred values of these three functions also for 0 degrees and 90 degrees.